about antiderivatives. And that's basically the opposite of taking the derivative. So you just look at a function and say, what function, when I take its derivative, is going to give me this function? So notational, we usually call capital F the antiderivative and little f the derivative. So the way that it works is when you take the derivative of capital F, you get small f. And then the most general one is going to be f of x plus c. Okay, so let me try to explain this. So here we have a bunch of functions, and they're antiderivatives, functions and antiderivatives. So basically, if you look at it, if you look at these ones right here, all these functions here, like for example, e to the x, its derivative is e to the x. Okay, sine x, its derivative is cosine. Negative cosine x, its derivative is sine x. Tangent's derivative is secant squared. So the derivatives of the things over here are equal to the things over here. Okay, but x to the n plus 1, all over n plus 1, its derivative is x to the n. Okay, so you kind of, so it's like in the point of view of making these ones the more simple form, and then these ones could be a little bit more complicated. So the negative is over here instead of there, for example. Because the derivative of cosine is negative sine, so the negative will cancel out and give you sine. So that's all that is about. And I think that one of the most important, or one of the best tools to, or techniques to use when you're finding antiderivatives is just to guess what it is. You know, think, okay, what function when I take the derivative is going to give me this? And make an initial guess, then take its derivative, and if you don't quite get the original function when you take the derivative, then adjust it until you do. That's one way to go about it. Okay, so let's do some examples. Oh, and let's do some examples, and I'll illustrate this idea as well. Okay, so number 1, find the most general antiderivative of the function f of x equals x squared minus 3x plus 6. Okay, so you take each of the pieces. According to the theorem on the previous page, you can handle each of these separately. Just as when you take the derivative, you're hooking each of these separately. Okay, so this one was x squared was x cubed. But when you take the derivative of x cubed, you have this 3 coming down, right? And then it reduces by 1 power. So if you divide by 3, then that's going to work. Okay, the derivative of this now, because when your 3 comes down, it cancels with that 3, and you just get x squared. This one, you raise this by 1 power, but then when you take the derivative, you're going to have a 2 come down. So you just put a 2 down here to eliminate that. And when you take the derivative of that, you're just going to get that. And then this one, 6x. Okay, now when it says general, that means you're going to add a constant on the end. Now you don't know exactly what that constant is, but the thing is, no matter what it is, so like if the constant is 5, then when you take the derivative of this, you're going to get that. If the constant were 7, then you take derivative of that, you're going to get that. So this is basically a family of functions. This antiderivative right here, the most general antiderivative. It's several different functions, packed into one. Depending on what you make the constant, you get a different function. Okay, great. Let's look at number 2. So you have g of t is this fraction right here. Now, the best thing to do is to rewrite it as separate pieces. Like that. And if you're taking the derivative, then you'd want to get, then these square roots are kind of cause you trouble. So you'd want to get everything in terms of power up in the numerator raised to some power. So like, for example, here, this is 3 over the square root of t. So that's 3 to the negative, it's t to the negative 1/2. This one, when you reduce this, it reduces to the square root of t. but we'll write that as t to the 1/2. This one, you got t squared over root 2. That's t to the 2 minus 1/2. That'll be t to the 3/2. Okay, now we're going to take the antiderivative. So we do this piece by piece. This first one, you want to raise this power by 1. So t to the 1/2, because negative 1/2 plus 1 is positive 1/2. Now, if you take the derivative of this, then when you reduce this by 1, you're going to get that. So you'll get this term here. But you'll also get a 1/2 coming out. And so if instead of putting a 3, we put a 6, then when that 1/2 comes out, then the 1/2 will reduce this 6 to a 3. And so we'll get that. Okay. Next one, you add 1 to that, so that's 3/2. Okay, now think, if you take the derivative of this, a 3/2 will come out. So if we put a 2/3 there, then that will cancel that 3/2 and we'll just get that. This one, similar thing. When you raise this by 1 so 3/2 plus 1 is 5/2. When you take the derivative, you'll have a 5/2 coming out. So if you have a 2/5 there, then that will cancel all that out and you'll get that. And then for the general part, again, we add our constant on the end. And so we have a family of functions. Each of the functions in the family, his derivative is g of t. Okay, and then this one you can rewrite as the square root of t if you want, or just leave it like that, either way. Okay, so all those should work. Now let's look at number 3. Find f if f double prime is 2x plus 5e to the x. So the second derivative is this. So we want to find the first derivative. We have to find the original function. Okay, so we'll start working our way backwards. The first derivative would be the antiderivative of this. So we look and see, okay, what function, when we take its derivative, is going to give us this. And the first term is, like, if you raise this, this 1, you add 1 to that, it's 2. So x squared. If you take the derivative of this, you have a 2 coming down, which is right there. So we don't need to put anything out here or divide by anything. Okay, this term, if you take the derivative of e to the x, you're just going to e to the x. So just put the 5 there. And then we want to add a constant on the end just for the general function. Okay, now next step, since this is the second derivative, this is the first derivative, now the original function. We take the antiderivative of this, so that's going to be x cubed. Now, when we take the derivative, we have a 3 coming down. So we need a 3 in the denominator to eliminate that so we can get x squared. Here, it's just going to be this. This one right here is a constant. So we need c times x, because if we take the derivative of this, we just get c. And then we'll put a d on the end. Okay, instructions said use c for the constant of the first antiderivative, which is right here, and d for the constant of the second antiderivative, so which is this one. Okay, so that should get you the correct answer. Great, now let's go to number 4. Here the derivative is 12 over 1 plus t squared. And they give you, this is called an initial condition. This right here helps you to find out what that constant is. And basically what it's saying is that f is equal to 0 when t is 1. So t is right here, so the function is f of t, right? So the 1 took the place of the t. And so f is equal to 0 when t is equal to 1. Okay, so we'll use this information a little bit later. But let's go ahead and take the antiderivative. And so you think about what function, when you take the derivative, is going to give you 12 over 1 plus t squared. And the answer is inverse tangent of t. Because when you take the derivative of the inverse tangent, you get 1 over 1 plus t squared. Okay, that's on the, I believe that's on the chart on the first page. Yeah, right here, this one right here on the first page. The derivative of the inverse tangent is 1 over 1 plus x squared. And so the antiderivative of this will be the inverse tangent. And of course here it's got t's in it instead of that. And then of course we have to put on the constant at the end. Okay, now this initial condition will allow us to find that constant. So we're going to put a 0 in for f, and we'll put a 1 in for t. Okay, so that's going to be 12 inverse tangent of 1 plus c. Now let's see. Well, we could probably say we could probably say, okay, what is the inverse tangent of 1? It's an angle. Or you could just like leave it like that. So c is negative 12 times the inverse tangent of 1. Okay, so inverse tangent of 1 would be an angle that's going to give you a tangent of 1. And that would be pi over 4, because pi over 4 gives you 1 root 2. So the tangent of pi over 4 is 1. Therefore, the inverse tangent of 1 is pi over 4. Okay, so that means that c is negative pi over 4. So then we plug that c into here, and you're going to get 12 inverse tangent of t minus wait. I made a mistake. I forgot this piece here. So there should be a 12 there. Okay, so that's going to be 12 divided by 4 is 3, so negative 3 pi. So minus 3 pi right there. Okay, great. If you leave it like this, it's also going to mark it correct, by the way. So if instead of like figuring, okay, that's 3 pi or negative 3 pi, you could just put minus 12 inverse tangent of 1. That'll also mark it correct. Okay, great. So now find f if f double prime, the second derivative of theta is sine theta plus cosine theta. F of 0 is 3 and f prime of 0 is 1. Okay, so let's start with this. We have the second derivative here. So now let's take one antiderivative. That'll give us the first derivative. Okay, so if you take the derivative of cosine, you're going to get negative sine. Okay, so if we take a negative on the front here, that will cancel that negative when we take the derivative of this. Okay, right here, if you take the derivative of sine, you get cosine. Okay, so this right here is an antiderivative for this one, and add a constant on the end. Okay, now this second one here means that theta is 0 when f is 1. Okay, so no, I'm sorry, f prime is 1. So you're going to put a 1 in for f prime, and you're going to put zeros in for theta. And of course, this is -1, and this is 0. So that's 0. So C, so break this over here, and C is going to be 2. Okay, so let's go ahead and rewrite this with the value of C. So now the first derivative is negative cosine theta plus sine theta plus 2. Okay, and then we're going to take an antiderivative of this. Now, if you have sine theta, the derivative of sine is cosine, so put a negative there, and then we're good to go, because the derivative of that's not going to be negative cosine theta. Here, the derivative of cosine is negative sine, so we'll need a negative here to make it so that when you take the derivative of this, you're going to get positive sine theta. Okay, and this one is just going to be 2 theta, and we'll have another constant. We'll call that d. And we'll use this right here to find d. So f is 3 when theta is 0. Okay, so we replace this f with a 3, and we replace the thetas with zeros. Okay, now that's 0. That's also 0. That's 3. This is -1. Cosine 0 is 1. And so then we add 1 to both sides, which takes this -1 over to the other side, which is a 4, as a positive 1. So, and 3 plus 1 is 4. So d is 4. And then finally, we take this d and plug it back into that equation. And we have negative sine theta minus cosine theta plus 2 theta plus 4. And that's going to be our answer right there. Okay, great. Any questions on anything so far?
What is d?
Where did the d come from?
Yeah.
Okay, that's when you take an antiderivative and you want the most general form, then you have to add a constant on the end. So it's like similar to when we added the c right here, but we just called it d. Okay?
Yeah.
So you'll be doing a lot of that, by the way, so that's really important. Now, this time as we went along, we had these initial conditions. And so the initial conditions allowed us to, right when these popped up, to plug in the initial condition and find out what they are. Okay, great. Yeah, so on the first page, wait. Yeah, so right here, it talks about it right here. Right here. That the most general antiderivative of f(x) plus c, where c is an arbitrary constant. And so then it was just d, where d is an arbitrary constant. You can use different letters. Like the most common, the first one you usually go to is c, but you can use other ones. You could also use c1, c2, c3, or just c and d and whatnot. Okay, number 6. Okay, so now here we have an application where with a stone being dropped. A stone is dropped from the upper observation deck of a tower 200 meters above the ground. Okay, so there you can actually get information from this. So let's consider the situation. Okay, so you're up on a tower here and you're dropping a stone is going to fall down, and it's going to be this is 200 meters right here, this distance here. Okay, so let me tell you what the important parts. The first one is that acceleration, which is the second derivative of position, is acceleration, which is negative 9.8. Negative 9.8 meters per second squared. So here we're dealing with meters. If we were dealing with feet, then it would be negative 32. Okay, but it's meters, so it's negative 9.8. That's gravity. Gravity is the acceleration. Okay, so gravity is the constant of gravity is the acceleration. Okay, and that's the second derivative. Then we have two statements right here. The stone is dropped, okay, from the upper observation deck, 200 meters above the ground. So this right here is telling you that the initial position is 200. So when t is 0, s is 200. This one is telling you it's dropped. This is telling you that its initial velocity is 0, or s prime of 0 is 0. Okay, so you got those two information. So those two are the initial conditions. Okay, now we have the second derivative is negative 9.8. Okay, that means that the first derivative is the antiderivative of the second derivative. And so the antiderivative of this is negative 9.8 t plus a constant. Now we know that the initial velocity was 0. So that means that we plug in 0 here and 0 for t. And that gives us 0. So the first derivative is 0. And then negative 9.8 times 0 plus c. And since that's going to be 0 and that's already 0, that means that c has to be 0. And this constant right here, by the way, is also known as v sub 0. So usually when you're doing this kind of a problem, this is v sub 0. That's the initial velocity. Initial velocity is 0. It's just dropped. It's dropped. It's not thrown in any direction. It's not given any initial. It's just dropped. So the initial velocity is 0. So v0 is 0, which is this c here. Okay, so that means when we plug that into here, that means that the velocity is negative 9.8 t. Now, to find position, we take the antiderivative. And when you take the antiderivative of t, you get t squared. Okay, but thinking about it this way, when you take the derivative of t squared, you have a 2 coming down. And you want to get a 9.8 there. So if you make this 4.9, negative 4.9, then when the 2 comes down, 2 times negative 4.9 is negative 9.8. Okay, and then, of course, you're going to have another constant over here. This other constant, we use this right here to find out. So we're going to plug in, so this 200 will go in for the s of t. And the 0 will go in for t squared. Okay, so that's telling you that d is 200. Okay, now usually instead of using a capital Z, you could use an S sub 0, which could stand for the initial position. Okay, but it doesn't really matter. So this 200 goes into there, and you have S of t equals negative 4.9 t squared plus 200. Okay, and this is the answer right here. Let me write that 200 a little better. Okay, so this is going to be the initial answer right here. Negative 4.9 t squared plus 200. That'll be the answer for part A. Okay, now part B. So how long does it take the stone to reach the ground? So what you do, this is always going to be your height right here, negative 4.9 t squared plus 200. That's going to be your height. So you set that equal to 0 to find out when it's going to reach the ground. And that means you take the 200 over to their side, and you get that. Then you divide by negative 4.9. Then you extract square roots. Now normally that's going to be plus or minus the square root of that, but since we can only have positive time, it doesn't make sense to go back in time. Then it's got to be positive the square root of 200 over 4.9. And it says round your answer to 2 decimal places. So if you put that into a calculator, you get approximately 6.39. So 6.39 seconds. Okay. Next part. With what velocity does it strike the ground? Okay, so at 6.39 seconds, what's the velocity? Well, we know the velocity is this right here. Negative 9.8 t is the velocity. Okay, this is the position, so the velocity is the derivative. But I mean, we got this from the velocity, right? So when it strikes the ground, it's at approximately 6.39 seconds. Or you can put this number in right here. Wait, 0.98? Well, how did I do that? That is just weird. How did I do that? It's 9.8, not 0.98. Okay, and I get approximately negative 62.61. Now, it's probably going to be more accurate if we put this in, but I don't think that Webassign will care that much. I probably put this in, actually. I probably put that value in when I calculated this. So negative 62.61 seconds, or this will be meters per second, and this is seconds right here. Okay, and then part D. If the stone is thrown downward with a velocity of 6 meters per second, how long does it take to reach the ground? So this time, it's thrown downward with a velocity of 6 meters per second. That means that the initial velocity is negative 6. And so what happens there is you come back to this part right here. You come back to that one. And you plug in let me get green. So you plug in a negative 6 for S prime of t, and you plug in a 0 for for t. This time. So this zeroes out, and you have c is -6. Okay, and so instead of what we got here, which is s prime of t is -9.8 t, and that's it. Instead of that, we're going to get s prime of t equals -9.8 t minus 6. Okay, that will be the s prime of t. Okay, and then you're going to take the antiderivative of that. So it's you still get -4.9 t squared, but then you're going to get -6t plus our d constant. This initial condition is still the same, though. This one is still the same. So you plug a 200 in over here, and you plug a 0 for t. And you get d as, you still get d as 200. You still get d as 200 because this is zeroed out. And so your position is now -4.9 t squared minus 6t plus 200. Okay, so the only difference is that here you have this -6t term. Only difference between this one and this one is here you have this -6t term. Okay, so now you want to know when it reaches, you want to know how long does it take to reach the ground? And the way to find out is you set s of t equal to 0 and find t. So you set all this equal to 0. And you use the quadratic formula. So that is -b. So A is -4.9, B is -6, and C is 200. So -b, that would be +6, plus or minus the square root of this squared, which is 36, minus 4 times A times C. So the minus is going to cancel with that minus, by the way. So it's going to be plus 4.9. 4 times A times C, so that's times 200. It's all over 2 times A, so 2 times -4.9. Okay, when you put this into the calculator, you're going to, so with the plus or the minus, you're going to get 2 answers. Because your answer has to be positive, and this is negative down here. This is negative. That means this term here is negative, which means you need this part here to give you a positive number. So that means that instead of plus or minus, you got to go with the minus. Okay, because otherwise, if it's just plus plus, then when you divide by this negative, you automatically get a negative number. Okay, so your only chance is to have a negative number up here in the numerator. Okay, because the denominator is negative, and so to get a positive number, you need a negative number up here. So minus is the way to go. And if you put that in the calculator, you get approximately 5.81 seconds.